We just had one of those cases where a computer, it doesn't work the first time, you do it a second time and it works. I hate that. That's not what computers are supposed to do. How are you, Ben, my friend?
I'm well. I'm happy to see you, and happy that it's working.
It's Friday,
think,
too.
I think what you've just proven, you've actually just scientifically proven that computers are insane. Because
and the operators.
People keep saying the definition of insanity is doing the same thing over and over and expecting a different result.
Well, it proved I was insane.
Inverse insanity with computers.
Right, because I had to do it twice and expect a different result.
we try to do the same thing again and expect the same result, and it doesn't.
Oh, my goodness.
Though. It's the ghost in the machine, but really the ghost in the machine is developers who can't leave the software well alone.
Well, that's it. The menu change.
So officially, to all my friends who build the tools that I use, I'm actually grateful that you keep developing them. So I'm just teasing. Okay, don't take it too.
Well, I look at it like, as a hardware engineer, I'm in a particular place where I can criticize programmers. First off, because I'm a hardware engineer. Second, that there's that symbiotic relationship. We need each other. They're welcome to criticize me as well. It's symbiotic is the way I look at it.
That's right.
So
they want to write the software using paradigms that they've used 1,000 times before and expect the hardware to behave.
Right. So speaking of random, because that's what we're talking about. Computers shouldn't be able to do random, and yet I just demonstrated that they can do a little bit of random. I've got a book coming out about the old days of Commodore, and one of the stories in the book is we tried to make white noise where a guy inside the chip created a bucket brigade of 256 stages and left the gates floating, expecting them to power up randomly. Well, I would have expected it too, but the reality was, due to the layout, the imperfections in layout and whatnot, it wasn't white noise, it was pink noise. It actually sounded like a bumbling freight train, like cha-chunga, dunga, 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 dunga. And he actually had to, for the next rev of the chip, he had to look up a random number and go into those gates going, you're a high, you're a low, you're a low, you're a high, high, low, high, and actually say, here's a random number for you. And he may have even looked up the random number in a publication called Rand Corporation, right? Because that's what they used to do. Was publish random numbers back in the day.
That is a weird thing to do. Be a corporation that just publishes random numbers.
But that meant they had a computer, a big one, in the background.
I guess those, you could probably join the dots.
Or they had a bunch of people flipping coins. That's the other.
It's a very long string, but you could join the dots to that and probably
eventually
blockchain technology. So, but random numbers, I would have thought back then, it would have been easy enough to use a CRC. I forget the name of the actual circuit, but you have an 8 or a 12 or a 16-bit shift register, and you have
modular.
A few taps off of that, which are XORed together, that feed back into the input. And that's what generates a pseudo-random bit sequence. But if you have enough stages in your shift register, if you have only a few, then the sequence repeats itself fairly frequently, and you get basically a exponentially more with each register stage you add. So you can, if you get 16 bits, you start getting a pretty decent pseudo-random sequence that is statistically pretty good for things like white noise
or good enough. Yeah. Isn't that how we generate Hamming codes and whatnot? If I remember, that's a bunch of shift registers with exclusive OR taps, if implemented in hardware.
Yeah.
Fire codes, those things.
So,
by the way, we're broadcasting on Facebook today. I thought I would try it as a new thing. So,
good.
Yeah. So before we get started, Coriolis-effect.com. The website's been moved. It's been updated. From there, you can find our Discord invite. You can find the YouTube channel, the YouTube links from there. I still don't know a way to have a link for all live Bill Hurd, Ben Jordan things. It's like we have to do a link each time. So if anybody knows how to find the link for literally a playlist, I'm all ears. But Google has not shared that with me. So what would you like to talk about today? I think we're talking about decoupling capacitors.
We were. This came up in the Discord. So again, I encourage people to join the Discord because it's been a little quiet this week because some of our members are younger and they're in exam time of the year before they graduate this year or this semester. So they're probably busy studying or doing tests right now. But yeah, definitely join that. Normally the discussion's pretty lively, and one of the things that came up as a possible topic or questions came up about was capacitors and decoupling, and separately, but on the capacitor topic, impedance matching. So those are maybe some things we could scratch on today.
Right.
And I think we should plan to do some more in-depth streams on those down the road, but we can at least jump in because something that didn't really exist 5 years ago, that the capacitor manufacturers have now started providing really nice online tools for getting accurate information about their products for impedance and measurement purposes. So I just quickly looked up a couple. I know I've used the AVX website quite a lot. I've used their information. So they've developed this thing called SPI Cat, or SPICE for capacitors. And we'll take a quick look at that. And then Murata is one of the other big capacitor manufacturers. They built this thing that's harder to find on their website. It's a little obscure, but it's called sim surfing.
Which sounds like a verb to me. Yeah, and doesn't sound like a simulator.
Yeah, it's just kind of weird, but it has a lot of detail, and that's what I'm looking at here. So I thought we could have a look at those, and I haven't tried yet to see if Kemet, Koa, TDK, or Panasonic, they're some of the other bigger capacitor manufacturers globally. I'm pretty sure most of them at least give you SPICE models for their caps, and you'd think, well, it's just a capacitor, right? Don't you just have the SPICE capacitor, and the SPICE capacitor model set its value and initial conditions? Yeah, well, that's idealized and not real. What you want to know is capacitors don't always behave like capacitors, and they may turn into an inductor at just the wrong moment. So they're very unpredictable. It's like streaming to YouTube. You do the same thing 1,000 times and you expect it to work the same way. They don't.
Yeah. Yep. So yeah, you just hit on it. A capacitor is a capacitor up to a certain point, and then what happens?
Then the equivalent series resistance and equivalent series inductance kicks in, and it behaves more like an inductor.
Right.
But first, let's bring it back. What kinds of caps are there, Bill? There's the most common we use, that's the cheap popcorn parts on every printed circuit board, are ceramic.
Yep. Well, I was around when MLCs, we used to call them MLCCs, when they first happened. Up until then, we actually used little ceramic disc capacitors, and if you didn't get a good one, like an NPO or something, they just basically stopped being a capacitor as soon as you put it in your refrigerator. So the temperature of a sandwich was all it took to ruin a capacitor. They were just hard to make good capacitors. And then MLCs happened, and we were like in heaven. And yes, and they had dip. They were set up. I can't
get it to focus on that. It's too small.
But they were small enough that you could put them right next to a dip. I mean, put it close to the dip, and we were like, it was heaven for us when MLCs came out. And they had wide voltage ranges. They went up to 35 volts, 50 volts. Matter of fact, the old AVX caps, the cheapest one was 50 volts. So suddenly you weren't trying to make that trade-off between, well, is 16 volts enough? Do I need 25? Just go with 50 or 35, and it blanketed it.
I'm just trying to find some of these older type caps out of the breadboard.
They came out with sockets for a while that had MLCs mounted in them. They don't do that anymore, but at one time we were buying dip sockets that had an MLC cap strung between pin 16 and 8. Right in the cap.
That.
You could
yeah.
What could be shorter?
Expensive.
I mean, the leads were only an inch long. I mean, it's like nowadays an inch is just horrible. Just horrible.
But basically, every chip had its own mini power and ground plane right under it.
Yep.
Because back then it cost a fortune to do more than 2 layers on a PCB. 4 and 6 layer boards were brand new and considered experimental.
Completely unreachable price. Yeah.
Only used for military or high rel sort of like specialized applications.
Yep.
And then there were these, the green caps.
Micas.
Polyester.
I love. Is that a polyester mica? Right.
I think this one's polyester, but there's mica as well. So those are different insulators, but the value of these, and I buy these still because these are what you want for audio, and the reason is they're less microphonic. So caps can move and flex, and if you hit a multi-layer ceramic chip capacitor and it vibrates,
yes,
and the dielectric vibrates, and it actually becomes a microphone. And some of the tiny little microphones now, like MEMS microphones, operate on that principle. And if you bias a capacitor on and attach it to a very high impedance, high gain input of an amplifier and whack the capacitor, you can, like, that comes through. You can hear it. And this is why high-end hi-fi audios companies like Lynn in Scotland make turntables out of granite, because the whole thing's on rubber, big rubber mounts, and it's all granite, and the turntable chassis is all granite, so the whole thing has very low vibration and is very stable.
Tubes are my chronic.
Yeah.
Also, you could tap on a tube, and because it's got that physical aspect, and it's even will vibrate in there, you can modulate the signal by tapping on the tube. Here's a cap for you.
Yep.
Right here, this big one.
Oh yeah, that's polyester.
That's a polypropylene.
Right. And those
because that's got the lowest dielectric absorption we could get back in the day. This is a dual slope AD converter. And when the slope went from going up to going down, we didn't want that little loss of the dielectric absorption to appear as error. So we use polypropylene caps, which are a fancier version of polyester caps.
Yeah. And they they also, if I recall, tended to have higher dielectric withstanding.
Breakdowns. Yes.
Yeah. So they were used in high voltage, but had less capacitance.
Right.
And like everything, these are all trade-offs. And of course, the other thing, this is just a piece of printed circuit board. Of course, you put copper in your board to get the capacitance for plane layers, but you get very little capacitance comparatively, but it stays capacitance into much higher frequencies, and that's something we were going to look at, which is kind of important.
Right.
Because
then, of course, the other cap that came out around the time I was in, it was already established, but it was tantalum capacitors. And back in the day, we were, I swear, probably 1 out of 10 would explode the first time you put voltage on it, but it seemed like 1 out of 5 would explode. And so my thing was, I was always putting a piece of paper over the circuit the first time I'd turn it on, because as we'd say, a piece of tantalum in the eye just ruins your day.
They tend to fail short, which is why they're spectacular.
Yeah.
There are other caps like film caps, polyester film caps. If you subject them to abuse, they fail, but they tend to fail more open. And now, like Weimer, one of their claims to superior product is they make high power, high voltage caps that are self-healing. So you can get dielectric breakdown just in one small place, but the way they've developed the polymers is they flow in and somehow reseal between the conductors.
Right.
Of course,
or even a hole punched in the plate. Yeah.
So eventually, there's only so much they'll take. Of course, any capacitor you can make it explode if you really want.
Right.
You've got to some make it work harder to get the pyrotechnics.
Isn't that part of the challenge with like lithium batteries? It's like, okay, we know they're going to short together. So what do we do when the two plates short together and they're trying to create different polymers in there, or create the chemistry such that maybe a short never exists in the way it does now, which causes explosions, you know?
Yeah.
So, but I haven't kept up with, you know, the current batteries is changing monthly. It seems like the lithium chemistry and stuff. I shouldn't say chemistry, but it's a very big deal. There was just a Nova on showing battery powered flight this week, and I do recommend it for everybody. They've gotten further along than I suspected, but I didn't know. And they're actually jumping in battery-powered airplanes that are certified as experimental and taking them for spins now and stuff. And they act just like a Tesla, right? That while they're waiting for another plane to take off, the propeller stops. And it's just weird because it's like, okay, cleared to take off, and the propeller starts up and off they go. So it's very cool. It was a good show.
I got to check that out. I haven't seen that. I had an associate from when I was at Altium, one of the co-founders, who's a pilot and into flight as a hobby, Dr. David Warren, who lives in Hobart, Tasmania, and he built, with a friend of his, a lithium battery powered ultralight. And there's YouTube videos. I don't have the link right now, but I'll share those in the Discord later. Of him doing some test flights in an ultralight, which is essentially it's a hang glider with an upright seat, tricycle, undercarriage, and some kind of engine mounted to the back that pushes it along, and you steer by tilting, much like you do just as hang gliding.
Right.
And it looks so fun.
Wow. Yeah, my thing with battery powered cars is, as you know, I used to do rescue work, and you know, when the airbag first came out, we had to go to the vendors would put on things to tell us why they're safe, and they're like, we would never put something unsafe in a car, and we're going, hey, you're putting gasoline and battery acid in cars, so don't tell us there's nothing unsafe in a car, right? These things are explosive.
There's a lot of things unsafe about cars.
Yeah, but now I'm you know, so I was trained to, like, you know, not kill the patient by setting off the airbag or putting a board in front of the steering wheel, which would get blown into the patient. But at some point, it's going to be, well, how do we keep these batteries from doing something strange while we're on scene? You know, I don't know what the answer is for that. How can you pull something to make the battery inert? That'd be ideal, but who knows, you know?
Yeah.
So
there's a lot
decoupling caps. Back to decoupling caps.
Right. So this is what we're looking at here with sim surfing. We can choose the different types. They have all their different types of caps they make in there, and other stuff too as well, I guess. So they've got the polymers, they've got leaded ceramic capacitors, so you'll get extra inductance there. But this is where you go if you want to get the SPICE models. And this would be, they call it netlist because it's a SPICE macro model. What these manufacturers are doing now is making accurate curve fitted models that give proper results. If you're using this part in a circuit and it's got equivalent series resistance inductance, you can do a very basic model of a cap, just having an ideal capacitor and some parallel resistance for dielectric losses and some series inductance and series resistance as well.
Right.
And you'll get better results than with the ideal SPICE model, which is only capacitive. But what
Right.
these companies are doing is they're actually measuring the devices in their labs and curve fitting proper models to those. And what I like about sim surfing, even though it looks like an eye chart or a spreadsheet, and it's kind of a little slow because of all the filtering that it does, but what they do give you is S parameter downloads. So I'm actually going to download that, and we'll have a look at that in my Smith program later. But if I want, oh, okay. So this is showing me the capacitor's
Wow.
response on a
Yeah,
Smith
let me
chart, a
zoom
mini
that
Smith
sucker in.
chart. I wish they made that bigger. I can download a PNG of that or print it out too by the look of it, or a CSV file. So that's pretty cool. I'm going to download the
Right.
CSV.
And it tells you what a Smith chart does right off the bat. It plots the capacitance of a capacitive reactance.
Not a capacitive reactance. What's that from? What's that from? That was a funny mock video about
Oh,
technobabble.
Yeah, I don't know.
So S11. So S11 is reflected, the view of the capacitor from the source.
Say something. We may have lost you. You may be coming back. You're frozen. There you are. You're starting to move. So, by the way, we blame this on sunspots. We don't know if they're sunspots today, but that's my excuse for the internet fading on us here. So, there you are. You're
There it
coming
is.
back.
I think I'm back now.
Yeah, it's funny. It now fast forwards to clean the buffer out.
That is so annoying.
And now you're back on VCam.
Yeah, I don't know why the camera started.
There you are. Cool.
You're
weird. Back.
That's weird. Sorry.
All right.
Technical difficulties. As always.
Well, it's that random thing we were talking about earlier.
That's right. We expect things to work as they always do, but they don't.
So, all right, continue.
So I want to download the S parameter file. So just for the selected part number, I'm going to download that. This should give me a standard touchstone format. Yep, S2P.
Which, again, you can also get from things like vector network analyzers. Will create one for you. If the manufacturer didn't, you can find your own, so to speak, and we'll talk about that a little bit.
Yeah. Yep. Let's switch to shunt. So looking at a capacitor in series, you can see it moved around the S parameter plot.
Right.
Around the capacitive side. So we'll come back to that. If I go to shunt, you'll see how it changes that behavior. It follows lines of admittance when you put a shunt capacitor. So adding a shunt capacitor moves things around the Smith chart in these to the circles of constant resistance capacitor side. But you can see above that it goes inductive.
Right.
If I switch back to series and look at it on a Smith chart, and why we care about 11 is that that's an indication of how well or something. Now, if you're just
say that part again. Your audio just cut out. So tell us what S11 does for us again.
We care about S because 11 gives us a measure of how well our impedances are matched in a circuit.
Right. Okay.
Yeah. So let me close that again. So this is series capacitance in a minute. And of course, at a certain point, it goes more inductive, right? The top half of the Smith chart means inductive. The bottom half means capacitive. So there is a point where the capacitor is behaving more like behaving like an inductor because of the equivalent series inductance takes over above that sort of frequency range. So in either case, we can download a SPICE model, get more data on the part. And so this is a really good selection tool if you care about how something's going to work in whatever the target circuit is. So similarly, I was checking out, and I like SpyCat a little bit more because although it has less detail and doesn't have as much available information right there in the website, it's kind of it's an easier user interface and it's easier to find. And what I did get stuck on today though was remembering where to go to get because this download here, I can get S parameters, but it's not giving me a SPICE model. And it may be that they don't offer those for every single capacitive family or value, but the SPICE model should be here as well. So I don't know why I can't see that. I'm pretty sure I've downloaded SPICE models from here before, but so let's have a look at this. So I've just selected one part.
Yeah, scroll down just a bit if you would.
Wait, I'll just go back to the selector. So if you're designing digital electronics, you need a few decoupling caps for a chip, and you look at the lattice part. You look at the manufacturer data sheet or reference designs, and they have, like for this. Oh, there goes my camera again. What the hell?
You're back.
Can you still hear me? Okay.
Yes, I can now. Yes.
Yeah. So looking at something like this and the decoupling, you look at a reference design and they've got 0.1, they've got 10 microfarad volt capacitors, then 0.1s for each of the power pins, and maybe 0.01s as well, like the decades in parallel kind of deal.
Right. Old rule of thumb.
And so you look on Mauser because you get to order some for a prototype, and you find your 0.1 microfarad caps on Mauser and in 0603, and you go, okay, well I'm gonna get, it looks like these Wi-Fi Vs are they're unbelievably cheap. So let's go for a Wi-Fi V 0603. And we'll go for 100 nanofarad. That's your 0.1 microfarad. And look at this. Okay, so there's two parts available. And we'll just select the 25 volt one because it's for a 3.3 volt supply. So we don't need the high voltage one.
Real quick, what's the difference between a Wi-Fi V and something like an NPO?
Aha. It's the different class of dielectric. So the actual ceramic polymer blend. So capacitors, for their insulation, use resins similar to PCBs, resin composites, but they use, instead of fiberglass inside, of course, it's ceramic powders.
Okay.
So we're talking alumina, that's aluminium oxide powder, the bright white powder. Some of them might use other metal oxides as high strength dielectrics that have because what they want is for this given size capacity, you want more capacitance. We always want more for less, right? So they build these dielectrics to have very high dielectric constants, so you get high capacitance. But the problem there, you still need some polymer to bind it together and keep the powder bound together. And there's the problem with that is not a perfectly homogeneous material, and there's different expansion and temperature characteristics. So the whole end of that story is this classification of dielectric is ultimately comes down to classes of what percentage of capacitance tolerance range you have over the usable temperature range. So it's really about temperature. But by very nature of the fact that they're changing what the dielectrics are by different grain sizes and different amounts of resin content versus grain sizes and different metal oxides for different purposes, not only does it change the capacitance versus temperature coefficient, it also changes capacitance versus frequency.
Right.
It also has an effect on that. And so if you, on this SpyCat, which is really cool, it's showing us this MLCC general purpose low cost Y5V tin terminated decoupling cap is a capacitor. This is the impedance over frequency, and a linear downward slope and impedance over frequency means capacitive. So that because capacitive reactance XC is 1 over 2 pi f. Yeah, 1 over 2 pi f c. So let's, I don't know if I can put a note on my screen for that, but you get the idea, right?
Yep.
So downward slope capacitive. But wait, at 10 megahertz, this is not gigahertz here, people. 10 megahertz, it hits its resonance, where its minimum impedance is at, if I put the cursor over here, it says 16.47 megahertz. And above that frequency, it is now behaving like an inductor. So if you're designing, let me ask you this question, Bill. If you're designing a digital board with an FPGA and you're intending to run the clock frequency of the FPGA at 200 megahertz, and it's going to be shuffling data in and out of the chip, it's got serial interfaces, maybe you have parallel connections to an SD-RAM device, where it's entirely possible for the entire address bus to go from all zeros to all ones at the same time, or all ones to all zeros is the more likely scenario as the address counter clocks around, right? What's going to happen with your decoupling caps on the board?
Yeah, your ground pin, more importantly, will lift as the inductance resists that change in current. And it's not even that, if you're clocking it at 1 meg, it's not the 1 megahertz that is your primary frequency, it's those edges.
Exactly. So all of those bits changing from a 0 to a 1 suddenly has all those driving gates, the output buffers are all turning on at the same time from the same power supply. And there's, at that point, your decoupling cap isn't a cap. At those transitions, it is an inductor. And so, to your point, the inductance resists the changing current. So it takes ages for all those output buffer drivers to switch on. And that's what limits your ultimate, like, you still need the decoupling cap, you still need to provide the DC current to all of those. So eventually, as they do begin to turn on with a slower rising edge, the energy does flow out of the cap and into all of those gates. But if you don't want your ground voltage to rise too high, that's called ground bounce, you have to provide lower impedance capacitance for those higher edge rates or frequency components of the signal. And this is why we started putting a 1 nanofarad in parallel with a 10 nanofarad in parallel with 100 nanofarad, because the theory or thinking was, well, the 0.01 kicks in first because it's got a lower impedance at the higher frequency because it's a lower capacitance, and then the 0.01 kicks in, and then the 0.1 provides the bulk after that. and then everything settles. You're switching, your transient's done, everything settles, and then they can all charge up again, ready for the next big transient. But it doesn't actually work that way. When it worked that way, all through the 90s and early 2000s.
Right.
But when you get to sub 100 micron silicon process, the edge rates are so much higher that the decade caps actually started. What we discovered was you'd get anti-resonant peaks between them, where the impedance was counterintuitive, but you can't just parallel up tons more caps and expect it to work better.
And right here is an example of that, just in this curve, where we've got the best performance is when this drops all the way down the impedance, but right after that is the anti-resonant point, and it suddenly peaks up. And if you have a bunch of these lined up together in the area you're trying to use it at, suddenly your caps, as you said, it's not a cap, it's an inductor, and it's peaking at the same time. It's getting energetic, is the way I look at it.
That's right. So with the semiconductor companies have changed their tack on that one and say, no, you're better off having a good modern low ESR, high quality 22 microfarad cap or 220 nanofarad, some other bigger value. These capacitor companies have worked hard to make better caps that have a lower ESR. And that will still function well. And of course, bear in mind, like we're talking impedances here. This is still, you may be up in the 200 megahertz zone, and the impedance is still around 1 ohm. It's not bad. It still can serve its purpose. You want to sort of set a target of being 1 ohm or less, right? And to look at that
is related to the amount of ripple current that we can tolerate, which we pre-calculated. We've said what's the sensitivity of the circuit to a change in its voltage, and that we state as a percent of that total voltage. And so we say, well, that means we have to have a certain amount of charge laying around to keep that from keep that ripple from deviating from. Yeah,
exactly. So I really love this SPI CAT tool. Is cool because it gives you all that. It gives you the ESR view, the equivalent series resistance over frequency. Gives you the variance of temperature. So we talked about that. That's the Y5V dielectric.
Right.
If you go down as low as minus 35 degrees C, so if you're designing a product that's going to be used in Canada in winter, it is no longer a useful capacitor at 35 degrees C. You've lost 75 or 72% of your capacitance. That's a big deal.
We did a product for Canada in the winter. It's funny you mentioned that. It was for milk trucks to go and pick up the milk from dairy farms, and they needed to measure the flow of milk to know, that it's flowing and everything. And we actually used the self-heating, what we would do is turn on the circuit and made sure the heat couldn't go anywhere. And so the circuit would actually heat itself up, and after a while it would work. But we actually had to do Canada in the winter time. Yeah, it was a tough environment.
Yeah, that's something you need to do. Sometimes these parts just can't work in low temperatures.
Or you have to derate them real heavily. Yeah.
Yeah, and I've seen aerospace boards where whole copper layers were dedicated to squiggly lines, just the whole layer filled up with squiggly traces where they just pass DC current through it to heat the whole product up.
Heating elements. Yeah.
While it's out in space. Yeah.
So we talk about decoupling caps though, but as chips got faster, they had to move the decoupling caps first onto the substrate. Aren't chips these days really hybrids? It's really a small PC board with even more parts on it.
Big FPGAs. Yeah, big FPGAs and micros are. if you're in a BGA package, the BGA package is essentially a printed circuit board with the die glued to it.
Right, right. And then inside the chip, I was talking to a chip layout friend of mine, and he just happened to say in passing, he's like, and then I sprinkle decoupling caps. I'm like, wait, stop, what? And he has a cell that if he has spare room as he's hooking stuff up, he'll drop a decoupling cell, which is metal, you know, the metal of the VCC over the metal of the ground. Yeah. And he drops those as little standard cells around to fill up the areas that he doesn't need. So I'm like, oh, that's cool. A decoupling cap is a standard cell.
Might as well. It's like you do the same thing in PCB design. We do it all the time. Yeah. If you have a 4-layer board and you've completed all your critical routing and everything, you've basically done power and ground, and there's this empty space left, and it's just a sort of generic digital board, you fill it up with ground and power polygons to add to that available capacitance and return path copper for your signal integrity. So, yeah, it's the same kind of concept. You mentioned ripple current before.
Hydroscopic. I need my glasses here.
Oh yeah, yeah. PCBs and really any insulator can pick up moisture is probably what they're asking about there, or mentioning.
Yeah. So, all right. Continuing onward here. Anything else in this decoupling? What's the next button over? There's ripple current.
You mentioned ripple current. So this is about how hot this is super useful if you're doing a power supply with a DC to DC. So last week, and if you didn't see it, people go back and watch the last episode. We talked about buck regulators, the most basic switching regulator, when we were talking sort of power supply options. But you have your output capacitance of a power supply is storing energy to filter it and give a steady stream of DC current to whatever the load is. The load may pull current hard sometimes and then not pull hardly any other times. So you imagine you've got a CPU or ESP32. Well, when I'm connecting to Wi-Fi or looking for a router, it's pulling all sorts of high current trying to transmit and listen for a Wi-Fi signal. And that all takes a lot of power. So it's pulling heavy current from the power supply, and then maybe it connects. Maybe I put it to sleep based on my software. It goes into a very low power state. So the loads are very transient. The loads change. It's not like a resistor. It's pulling current and then letting go. Also, the power supply, if it's a switching regulator, it's sending current. It's charging up an inductor and then letting it discharge into the capacitance and then charging it up. And there's a freewheeling diode in that circuit. We talked about all that, how that works last week.
Right.
So that also contributes to ripple current. So ripple current is whenever energy is being dumped into the capacitor, that's positive current flow from the capacitor's point of view. And then when there's nothing coming in but the load is pulling, that's outgoing current, so negative from the capacitor's point of view. But either way, it's current. And so if you take the absolute value of that changing current, and you say if you have, so in this case, a 100 kilohertz is the red. So if you have a lower frequency, 100 kilohertz might be typical of a DC to DC converter.
Right, right.
So that's the red line. If I have as little as 400 milliamps at 100 kilohertz ripple, so a triangle wave of 400 plus plus 200 minus 200. If I'm doing 400 milliamps ripple at 100 kilohertz, this capacitor is going to have a 10-degree temperature rise, which is pretty significant. So caps and cheap dielectric caps like Wi-Fi V, this is also where you've got to relate this back to the dielectric you've chosen, because you're going to heat up your capacitors, and then that's going to change their capacitance as well as just generate losses. And so that's another reason why you may choose multiple caps and parallel them up as well, is to distribute ripple current and reduce the temperature rise in the circuit. So that's a kind of interesting one. The other one is DC bias. People tend to forget. You think a 10 microfarad cap is a 10 microfarad cap all the time. It isn't. If I have a 100 nanofarad cap, it's only 100 nanofarads before I've charged it at all. When it has zero net charge, then it's 100 nanofarads. That's its capacitance for charge. It's a tank for charge, for holding charge. And the more you fill up that tank, the less room there is to hold more. So naturally, as you put a DC bias voltage, as you put a voltage on a cap, it may be a 100 nanofarad cap like this one, but if I put it on a 12 volt power supply, this particular one, it's a 25 volt cap, but at 12 volts, I've already charged its dielectrics to, 72% of what they can be charged to. And so it's no longer a 100 nanofarad cap, it's somewhat less. It's 72% less because it's already charged, it's already got a bias. So, these are things you just don't think of these when you're actually sitting there designing your PCB layout, but you've got to think about them if you want to minimize, like that, how we do it, we just use rules of thumb, or we copy what someone else did in an application note or data sheet, and it just works because it's what they did and it's what they used in the lab, and it just works, right? Most of the time. But if you run into trouble, then these are some of the reasons why you can run into trouble. It's also the reason why there are labs in China where you want to get your product ready for mass production in a big factory. They'll plug your prototype in and start removing caps until it fails, and then they'll put the last one back on.
Right.
So,
that's called cost reduction. Yeah.
Yep. And it's
cost reduction by suicide.
We tend to way overdo things like decoupling caps because the caps are cheap, and it's easier to way over design it than it is to think about these things and actually calculate what's needed and figure it out that way. But then as a result, we get into these horrible situations with component shortages because everyone's overdone all their circuits and they're using too many parts.
Right.
Crazy.
So I always considered rules of thumbs part of an iterative process. Like you got to start somewhere, so you use a rule of thumb, but then then you go in and you calculate it full circle and try and understand what you do need in there. And as often as not on low speed stuff, my rule of thumb was good enough.
Yeah, and for small projects where you're basically going to build a prototype and then
throw it in the drawer. Yeah.
See how it goes on Tindy. It's also fine.
Yeah.
But it's like if you're a professional designer and you're going to do a consumer product that you're going to make hundreds of thousands of them, you want to think about this stuff because you can save a lot of time and money if you do it right up front.
So you mentioned Tindy. Tindy's now owned by somebody else these days.
Yeah, I didn't like that. I don't want to. It hurts my feelings. But Supply Frame got acquired by someone else.
Siemens.
Yeah.
Siemens? Yeah.
Yeah. One of the hulking giant gorillas, the incumbents acquired Supply Frame, and hey, you know what? The Supply Frame team have worked hard to build that business, so pats on the back to them. I guess they deserve what they get.
I've heard they're going to leave Supply Frame alone. That's all I've heard.
I hope so, because marketplaces like Tindy give
and Hackaday underneath Supply Frame also.
Yeah, they give us a lot of outlets, but more than anything, they make it even possible for people who've been in stifling corporate careers for a long time, an option to try something entrepreneurial. And the world needs those things. That was a good
push the boundaries.
It's a good service. Yeah.
Show us this circuit here.
So
that's not just a simple cap anymore. Looks complicated.
Yeah, this is the equivalent circuit, and again, I don't know why I can't seem to find the SPICE download, but normally you can download the SPICE simulation model. So it'll run in LT SPICE, it'll run in Fusion, it'll run in whatever front end you put to NG SPICE. But it's not even a basic realistic model where you have equivalent series inductance and capacitance and resistance included. It's actually a very detailed model that matches the plots we've been looking at. So yeah, there's some parallel resistance added to the main bulk capacitance, and that represents dielectric losses, and that can be more or less known based on the dimensions and the material they're using. So C0 is the main capacitor value here. That's the target value of the part. So C0 it's actually 144, but remember, capacitors in series reduces the capacitance. So that's up at 144 because there's all these other additional series capacitances in the curve fitted model. So what we're looking at here is complex because they actually measure the caps in the lab with really expensive, high quality test instruments. They characterize each capacitor, and they measure hundreds of them, and they get a statistically accurate, normalized model of this capacitor's response to temperature, to DC charge, equivalent series resistance, ripple current, and the overall impedance. And the net result of all of that is they have a curve or a surface plot, and they can curve fit essentially the normal 25 degrees C operation temperature, and they can curve fit this model by varying these resistance values and capacitance values to that lab measured set.
Right.
And so
now I see a non-lump sum where it says R3 to R11, ... Is that due to the physical layout, or do you think there's 12 layers of cap, the way the cap is folded over, or do you think that's just an artifact of the way they measured it?
I think that's really interesting that you asked that. And I don't know. I'd have to ask someone from AVX why they came up with 12 stages of a resistor and cap in parallel.
For this one, yeah. I wonder if different sizes, if they go down or up based on the number of folds.
Yeah, my guess would be that they add more of those stages in for getting more accurate curve fitting. So they probably have some sort of algorithm or Excel spreadsheet that they use to do the solve, and and by adding more stages, they get a more accurate curve fit.
Right.
So I'd say that's probably what they're doing. But that's a guess. I'd have to ask someone from there. So again, let's download the S parameters for series. I'll just save that file. Oh, that's the series S parameter, and let's download the shunt S parameter file. What's that you're looking at up there in the corner,
They're
Bill?
talking about turbo encabulators on the chat thing, so I just thought I'd throw it up there. I don't know what that is. They're taking the time to chat about it. I thought I'd put it up there. Whoops, looks like we lost you. So what is a turbo encabulator, everybody? Go ahead and tell me. I assume I don't know. All right, looks like you're coming back, Ben.
Am I back yet?
You're almost back. We see the VCam, so that means... Oh, and we see a Smith chart, so your screen share is working.
Yeah, and you can hear my voice?
I can hear you now. Yep, you're moving.
Okay. I don't know, what the heck is this? It's hard doing a stream across the country.
Yeah, we take it for granted, don't we?
Man, it's frustrating. But what I don't understand, I think it may be a software problem on my end, because when my camera dips out, the lights on it turn off.
Oh, okay.
The LED turns off, which indicates the software has stopped using it. But yeah, got to find a better way, or maybe I'll set up a different computer just for our show. I think I should do that. Yeah,
well,
so
it's actually, look at the time actually too. So
I know we're just about at the top of the hour, so we'll just finish off with this, but we'll come back in here and do more in future episodes. What we're looking at here is a Smith chart, and for those who haven't used them before, pretty much every electrical engineer learns about the Smith chart. A lot of people I know are electrical engineers, learned about them in college or university.
All right, so we lost Ben again. So the way the organization of a Smith chart, as Ben's been talking, left to right is resistance, capacitance follows these lines below it, and when something's inductive, it appears above the line. Oh, I can see him moving his cursor. Now we've got the Skype symbol.
Yep.
Maybe we're done for the day. We might just be done with our transmission for the day.
I turned off my video because something weird screwy going on there.
Well, that works. Go ahead. I'll make you full screen. Yep.
Yeah, let's just load up one of those S parameter files I downloaded, so we can see what it looks like on the chart. Let's go to quick access.
Somebody asked if you're using a C128 for the stream.
Yeah. That might work better, actually.
So I didn't want to say that. I was the one guy that didn't want to say that. Yeah.
So this is a shunt. I think I picked the shunt file. So this shows the reflection and angle of reflection and magnitude of reflection and transmission angle at all the different frequencies for a situation where this capacitor has been put in parallel with the circuit, right? So it gives me a whole lot of data points, and they've gone all the way up to probably 10 gigahertz or something like that. All right, so I'm going to select all that and hit OK. And it plots the whole thing on my Smith chart. Each one of those lines in the spreadsheet is a data point. And so I see the data points in here, and I expect it on this side.
I think we lost your audio. Move your mouse around a little bit. You're back. Go ahead.
I'm scrolling down through the data points looking for 100 kilohertz, or close to it. Here it is, 100 kilohertz. If I select that data point, you can see that's selected there. I can zoom in.
Well, the good news is it's capacitive at 100 kilohertz.
Yeah, that's the point right there at 100 kilohertz.
Right.
So the impedance of this capacitor varies over frequency in parallel with a source that's driving a sine wave into it. The impedance of the capacitor at 100 kilohertz which is in the list of data points, right? Well, I'm up in the gigs again. Come on. Why am I so slow? 100 kilohertz. The impedance is 4.915 minus J. So minus J is the reactive component. That's your capacitance. JXC. XC at that frequency is 14.028. And 4.915 is your DC equivalent series resistance at that frequency.
All right.
Yeah.
So what's that telling us its impedance is with the total of those two elements?
The impedance is 4.915 minus J14 ohms at 100 kilohertz. So what it means is...
I couldn't see the 14. Okay, very good.
Yeah, it's a tiny number on the screen. I apologize. And so you can look at this and go, well, if I need a capacitor for an antenna matching circuit, and my antenna's at the, like you could say, my antenna's at the 420 to 450 megahertz band. You want to know if you're using a capacitor in an impedance matching circuit, that its impedance is actually useful in that band, and you could start by knowing what kind of ideal capacitor you would need, but then you have to find one that matches that closely at the frequency of intended use.
Right. So maybe next week we can talk more about Smith charts and actually show how to get from one spot to another, which is known as, antenna matching. If we start with one spot on here, how do we get over to the value needed?
Right. Yep, we'll do that.
All right.
And
yeah, see if you can turn your camera back on.
Doing something at 2 gigahertz or 3 gigahertz.
Here you're coming back. All right. Well,
yeah. Next week.
Yep. So go ahead, turn your camera back on so I can say goodbye to you here.
I'm trying. I'm going to stop the screen share.
There you are. Yep. Very cool. You're back.
I'm back.
So what's your T-shirt today? What is that pattern? Is that a nanoball or what is that?
I don't know who designed this, but it's from an album cover from a musician I really like called Tony McAlpine.
Okay, cool plug.
He's into different patterns and stuff. He has a couple of different album covers that have repeating circular patterns like this.
Well, I'm trying to relate it to music. Like, what would a D suspended fourth look like if you plotted it in a 3D sphere as a...
Oh. Yeah,
so
it might look like something
cool.
like this.
Yeah, it might. Who knows? All right. Well, hey, it was great talking with you. As usual, we didn't get all the way through the material, but we learned a lot about decoupling cap construction. That was there's stuff in there I never knew before about the materials and stuff. So that was very cool. So,
yeah.
What should we talk about next week, though? Maybe more Smith chart?
Yeah, well, we should lead off here since it's where, and for me, well, actually, Bill.
Oh, you won't be here next week. That's right.
I'm out for 2 weeks, unfortunately. But you were going to work on having.
Well, I'm going to ask some people. We'll figure something out. Yep.
And when I'm back, we'll kick off with Smith and go through a whole couple of scenarios of how we do impedance matching and where to use discrete components versus actual elements of the PCB trace instead, because it's going to be more practical in some cases.
Right.
Yeah.
Well, cool. Very cool.
It's good to
well,
see
hey,
you, man.
again, my friend, good seeing you, and I hope you have a safe couple of weeks there, and we'll catch you in